So I hope you found this project to be rewarding. It was an opportunity to finally apply a lot of different techniques that you've learned in this course to a real-world problem. And I personally found it pretty exciting to actually try to apply this stuff to, a field of medical research that might actually make people's lives better. Anyway, let's take a look at how I did it, and you can compare your results to mine. If you open up the mammo_masses_project file in your course materials, you can sneak a peek at my solution to it. And there's a lot of code here, so I'm not going to go through every single line one at a time, but you can always take a look at it in more detail yourself. High-level overview, a lot of the work is just preparing the data. That's just the reality of life as a data scientist. So I started off by just reading in the data file naively, as is, and I saw by visualizing that resulting pandas data frame that the column information was missing. I have to do something about that. There's these question marks in there that I have to deal with, so I tried it again, this time specifying that question marks represent missing values and passing in an array of column names so I can actually get the proper column labels on there. And things look a little bit better now, but we still have all these missing values that we need to deal with. I did a describe to get a handle on how bad the problem was, and you can see that for density in particular, there's only 885 values in this entire data set. Widely different numbers of counts for different columns, so there is some missing data that we need to deal with here. Now, we want to make sure that by just dropping rows that have missing values, that we're not introducing some sort of inherent bias into the data by doing that. So just to eyeball the distribution of that missing data, I did this little block here to actually pull up any rows that had missing data in either of the 4 feature columns. And I came up with this. Just by looking at it, they do look pretty evenly distributed to me, so I feel okay about just dropping those rows entirely. We can just do drop NA on that data frame to get rid of them, and do a describe to confirm that we do have the same count across all columns now. So we have a much cleaner data frame to work with now. Now I'm going to extract these into NumPy arrays that I can actually feed into scikit-learn. So I'm going to pluck out the feature columns and then use values to convert that to a NumPy array. I'm going to pluck out the label column, the severity column, and convert that to an all classes array as well. I'm also going to keep this array of column names around for later use and take a look at the resulting all features array to make sure it looks right. Sure enough, it looks like 4 columns of 1 feature apiece, one for each mass that was recorded. Next, we need to scale that data down, and like I gave you a hint, just use preprocessing.standard scaler for that, and we can eyeball that data as well, and it does look normalized to me at this point. So that's an important step for many of these techniques. For example, SVM and neural networks really depend on that to work properly. Started off by doing decision trees, and just going back to the earlier lectures on these topics, you should be able to convert what you saw there to this problem without too much trouble. But first we needed to create a train test split. We're going to do train test initially on the decision tree here. So I used model_selections train test split function to do that. Gave it a consistent random seed just so you can duplicate my results here if you want to. And scikit-learn makes building classifiers pretty easy, and it's always pretty much more or less the same format. So we'll start off by making a decision tree classifier with a given random state to start off with. Fit that to our training inputs and our training classes that we extracted from train test split up here from our entire feature set. And we will then just go ahead and, after fitting it, after doing that actual training, display it. This is just using a similar code snippet that we did back in the decision tree lecture. We can see we ended up with something really, really complicated. And the sheer complexity of this resulting decision tree might be nature's way of telling you that a decision tree might not be the best solution here. Why does it have to go to all these gyrations to get a reasonable result? That kind of tells you that the features that we're dealing with might not be split so easily. We can actually measure the result of this particular classifier by calling score on it with our test data. And sure enough, we're only getting a 73% accuracy on our test data set with a decision tree. So decision tree, not so hot. Let's go ahead and move forward to k-fold cross-validation instead of a single train test split. That's going to be a better way of evaluating these things. Maybe we just got unlucky with our split. We'll use cross-val score instead using our classifier model, and that will automatically do the training stage for us and then do the testing for us as well on 10 different folds of the data. And by computing the mean of all of those accuracies, we end up with a score of still 73%. So sure enough, decision trees are only going to get us to about 73% accuracy on this data set. How about a random forest? What if we actually use a random forest to try an ensemble of decision trees? Well, turns out that does a little bit better with 75%, but still not great. Let's move on to SVM. Start off with a linear kernel, see if that does better. Very easy to do. We're just going to set up an SVC model with a linear kernel, And at that point, we can just pass the model into cross-val score, pass in all of our feature and class or label data, and it does the rest for us automatically. Very easy to use scikit-learn in this manner. So yeah, in just 4 lines of code, we set up an SVC model. We did k-fold cross-validation with 10 folds, and we computed the mean error from k-fold cross-validation. This time we got up to 79.6%, so we're doing better than decision trees already. How about KNN? One of the most simple algorithms out there. There is actually a k-neighbors classifier available in scikit-learn. So again, it's just 3 lines of code to actually set up a KNN classifier on this data and measure it with k-fold cross-validation. That did surprisingly well, 78.5%. A little bit embarrassing that something as simple as KNN could actually outperform decision trees on this data. That's a surprising result. Now, we know that KNN is sensitive to the value of k, so you might want to try different values of k and see how it does. In this example here, I actually iterated through k values of 1 through 50 and saw if there was sort of a sweet spot to be had there. And it looks like things did kind of max out at around 79% accuracy, so can't really improve on that too much. Once you got beyond, around a k of 11 or so, things just sort of like sat there and didn't really get much better. How about naive Bayes? We can try that as well. We need to first pre-process our data using min-max scalar for multinomial naive Bayes, but at that point, it's just like any other scikit classifier model. And for that, we got 78.4%. So that's in the running. That's up there with SVM and KNN so far. How about different kernels with SVM? We can just try this again with different kernel types. So instead of linear, we can just run this 3 more times with an RBF and a sigmoid and a polykernel. You can see that RBF is doing pretty well. We're up to over 80% now. So far, the winner is SVM with an RBF kernel. Pretty cool. Shows you the importance of hyperparameter tuning. That choice of kernel can make a really big difference. So we've tried some pretty fancy, fairly complicated techniques here, including naive Bayes and SVM. These are all, pretty complex algorithms. What if we just keep it simple? Well, it turns out there's a technique called logistic regression, which is just regression that's made for classification problems. And at the end of the day, this is just a binary classification problem. So let's just throw logistic regression at it. It seems like the most straightforward approach. Also very easy to try out with scikit-learn, and by trying it out, we actually got a really good result of 80.7% accuracy. That's actually the winner so far. I mean, to be fair, a lot of these algorithms are giving us around 79 to 80%, so it's really a multi-way tie if you ask me. But logistic regression is a simple approach to the problem, and a lot of times, simpler is better. On the flip side, we can also try a neural network for this thing, see how that does. And here's what I ended up with. I actually tried a lot of different topologies here. This is what I ended up settling on. Turns out you don't need a whole lot to do this. All I ended up with was a very simple neural network with a single layer of just 6 neurons in it. And that was able to give me about 80% accuracy, which is comparable to the other good algorithms that performed well for this problem. Just to dive into it more deeply, we're using the Keras layer of TensorFlow's API, which is now available in TensorFlow 1.9 or greater. Creating a sequential model, we're just adding in that single dense layer of 6 neurons with 4 inputs going into it with a ReLU activation function and normally distributed random initializer values. We then have a single output neuron there with a sigmoid activation function, and we are using the binary cross entropy loss function because this is a binary classification problem and the atom optimizers seem to work best for me. Now that we have that model created, we can use the scikit-learn wrapper for Keras and import the Keras classifier. Use that to build a estimator that can be used with scikit-learn. With the model we created, we'll run it with 100 epochs and no verbosity. Pass it into cross-val score to actually measure how good this thing is. And again, we end up with about 80%, which is kind of interesting. So do we have a winner? Not really. Pretty much everything came out at around 80%, 79 to 80% accuracy. So it's really a pretty big multi-way tie with the exception of decision trees. Decision trees did not do well at all. So the only real loser we have here is decision trees, but everything else did pretty well. So if it were up to me, I would keep it simple. If you have a choice of algorithms that are equally good for a problem, stick with the simplest one. And for me, I think that's probably logistic regression here. And if you want to go back and fiddle with things some more, you might be able to squeeze some more performance out of one algorithm or the other by doing additional hyperparameter tuning or trying different topologies of that multi-layer perceptron in the neural network example. But at the end of the day, you're going to be hard-pressed to get more than 80% accuracy out of this particular data set. Anyhow, I hope you found that exercise very enlightening, and it's an opportunity to apply everything you've learned in this course to a real-world problem that has real-world applications. So, yay, I think that's a pretty rewarding end to this course. You've actually had a chance to try a lot of the different machine learning and data science techniques that we've covered in this course and applied it to a real-world problem that could actually save lives if it were used for real. So congratulations, let's move on.